Here are 4 points: 0, 0, 0, 1, 1, 0, and 1, 1. By randomly changing the position of this line, how do we divide the 4 points 0, 0, 1, 1 and 0, 1, 1, 0 into 2 categories? How on earth can we separate them? About with these 4 points, I brain my brain, task my mind, and rack my wits. It's no use just change the position of the line. We have to change the whole space, that is, the position of the coordinate system. In his book, The Name of the Rose, Umberto Eco said, "The order that our mind imagines is like a net or like a ladder built to attain something, but afterward you must throw the ladder away because you discover that even if it was useful, it was meaningless." What we just dealt with is artificial intelligence in solving XOR problems. We have started the prelude, but we're still a few steps away from the finish line. After watching my video, you are free to build a neural network and just watching our machine solve this problem automatically. Calm down. Let's take a look at the standard structure of this simulated neuron. Each input data is multiplied by a weight, and after they are added, a threshold B is added. If the result is greater than 0, it outputs 1, and if the result is less than 0, it outputs 0. The essence of this structure is a binary classification. If there are 2 input values, it uses a one-dimensional line to divide the 2-dimensional space into 2 pieces. If it has 3 input values, it uses a 2-dimensional plane to divide the 3-dimensional space. If it has 784 inputs, it uses a 783-dimensional hyperplane to divide the 784-dimensional space. However, no matter in which dimensional space, this classifier is too straight to deal with the situation of data crossing. For example, 0, 0, 1, 1, and 0, 1, 1, 0. These 4 points that we just try to classify. If we can bend this line, we can easily separate it. But it is pity that we can't bend this line because of the data x1 and x2 we enter are linear. The relationship between output and input is a linear function. Reflected in the 2-dimensional space, it must be a straight line. For a long time, this was considered to be the fundamental flaw in the perceptual model, until people realized if we can't bend itself, we can bend the whole coordinate system in the middle. Let's add 2 new neurons to connect them together. In this way, there is an additional intermediate layer between the input and output. The meaning of this intermediate layer is to change the coordinate system. Do you remember the examples of crocodiles and snakes in the last episode? Abscissa x1 is body length. Alternate x2 is body weight. After adding 1 layer, abscissa x1 becomes C1. Alternate x2 becomes C2. In this new structure, C1 equals x1 times W1 plus x2 times W2 plus B1. C2 equals x1 times W3 plus x2 times W4 plus B2. We can temporarily let C1 equals x1, C2 equals x2. At this point, W1 and W4 are equal to 1, and the other parameters are 0. Everything looks fine now, but if we start to adjust the weights of W1, W2, W3, and W4, something miraculous will happen. For example, when we adjust W1, we can play with the coordinate system horizontally, make it wider or narrow, or even flip it horizontally. And if we just W4, we will change the coordinate system vertically to make it taller or shorter. Then let me try to adjust the other parameters. Adjusting W1, it will change in this way. Adjusting W2, it will change in that way. Why? In essence, because Z1 replaces X1 as a new abscissa. According to this formula, the abscissa of every point in the original coordinate system will be transformed to a new position. For example, Z1 equals 2 times X1. The abscissa will be twice as wide as before. It's easy to understand, right? Similarly, W3 and W4 have the same effect on alternate Z2. Okay, now let's try to adjust these W and B to see if we can separate the 4 points. In addition, adjusting W5, W6, and B3 here can change the position of the straight line. No matter how hard we try, we can't keep it apart, because no matter how you adjust it, it's a linear transformation and it looks straight. The solution is actually simple. Add a layer of nonlinear transformation. Let me introduce activation function. You can think of activation function as a new rule that allows input data to be output in more regular way. For example, we talked about the step function in the case of crocodiles and snakes last episode. If it is greater than b, it outputs 1. Less than b, it outputs 0. If we move b from right to the left of the equation, that's what the step function really looks like. If fx is less than 0, then y equals 0. If fx is greater than 0, then y equals 1. If we represent it in the coordinate system, it looks like this. Isn't it easy? In our neuron structure, the step function is used from Z3 to the final output y, whether it is crocodiles and snakes or classified digits. We use the step function as an active function on the last layer. In addition, in machine learning, there are 3 common activation functions: logic function, linear rectifier function, and hyperbolic tangent function. We just got abscissa Z1 and ordinate Z2. Now, we can use a kind of activation function to convert them into H1 and H2. Between Z1 and Z2 and H1, H2, choose any activation function can actually solve the classification problem. If we add step function here, the coordinate system doesn't seem to exist. Abscissa H1 and alternate H2 have only 0 and 1 values. Think about it. How do we classify it? Now, let me try to separate these 2 kinds of ports with a step function. In this case, through the previous linear transformation, I can transform 0, 0 and 1, 1 to the position where the abscissa is less than 0. The abscissa of 0, 1 is less than 0, and the ordinate is greater than 0. The abscissa of 1, 0 is greater than 0, and the ordinate is less than 0. At this moment, with the step function, then on the new H1 and H2, 0, 0, and 1, 1 will be transformed to the position of 0, 0, and 0, 1 will become 0, 1. Concurrently, 1, 0 will become 1, 0. For the time being, we can adjust W5, W6, and B to change the dividing line and separate these 4 points. In fact, it is not intuitive to use step function to change the coordinate system. The other 3 activation function is much more dashing. For example, this way, or this way. We can also try the other 3 activation function. Now, they can classify these 4 points. We tried a lot of things, but that didn't work. Let's try prelude. Rectify linear unit. It will be more convenient to separate these 4 points. Squeeze the first kind of points into the corner and separate them with a dividing line. Finally, we managed to solve the classification exclusive OR problem. In retrospect, it was actually quite simple. First, set the activation function to deform the coordinate system, then separate the data by the linear transformation of W and B, and finally adjust the partition line equation to complete the classification. Let's challenge a more complicated problem. There are 60 dots, 30 white dots as one group, and 30 black dots as another group. Let's try and see if we can separate 30 white spots from 30 black spots. As you should have noticed, it is actually difficult for us to separate 2 rings in a 2-dimensional plane. But the solution is also simple. Add a dimension to turn a 2-dimensional plane into a 3-dimensional space. On the basis of 2-dimensional inputs x1 and x2, we can construct 3-dimensional z1, z2, and z3 by adding 1 more neurons to the middle layer. Now, we can not only transform z1 and z2, but also let every point in the original space get the value of z3. z3 equals x1 times w3 plus x2 times w6 plus b3. Now, let me adjust the angle of view and complete the classification of these dots in 3-dimensional space. Because we add a neuron, the way they are separated is no longer a line, but a surface. But it is still arduous task to separate these 2 types of points. Let's first set a goal to use one surface to make the differentiation of the 2 types of points, let's say, reach 80%. Just like this, let's put this class of points into a corner formed by 3 surfaces, and they are separated. In his book Zen on the Art of Motorcycle Maintenance, an inquiry into values, Robert M. Prig says, the solutions all are simple after you have arrived at them, but they are simple only when you know already what they are. Although we have reached 80% of this distinction, let's keep up our effort to bump it up to 100%. What I just did was dimension raising. Make the original dense data sparse in high-dimensional space so that they can be better separated by us. At the points above the partition plane, the output is greater than 0. The machine will adjust them to 1. At the points below the partition plane, the output results are less than 0. The machine will adjust them to 0. We can also project the classification of this three-dimensional space to a two-dimensional plane. The dividing line between the two types of data is a circle. The rest can be done in the same manner. We can also have 4 or 100 neurons in the middle layer. Let the input data be sorted in a dilute 100-dimensional space. But I can't show you what these points look like in high-dimensional space. To visualize, I will show you the classified data in a colored way later in my sequel. In fact, it is to calculate what you'll get when you input each point in the original coordinate system into the neural network. 0 is blue and 1 is yellow. The boundary between the two colors is the dividing line. The original XOR classification is distorted. After projection, the coordinate system will be straightened and the speed line will bend. But we'll know that the real dividing line must be straight. Next, we need to try this new structure on the machine so that our machine can automatically classify these 4 points like it classified crocodiles and snakes. But before I do that, I will show you how do I climb a mountain.